All right, guys, welcome to Statistics for April 16th. Apologies for the little bit late video today. What we're going to do in this video is take some data, some actual real-world data, and put it into use with sampling distributions like we've been talking about over the last couple of days. So I'm going to show you a web page here. This is the Missouri Health and Senior Services web page that talks about our coronavirus infections and just some information about it. And I want to point out we have 5,111 cases in Missouri right now, and we have tested 50,432 people. Now, we are going to treat this as if it is a experiment or a survey of sorts, a data set. So I'm going to write here that we have cases of 5,111, and we have had how many tests? 50,432. So we are going to treat this as a data set where we say we want to know how many people in Missouri have this, even outside of maybe the people that are tested, right? Like how many cases, what proportion of Missouri citizens have the coronavirus maybe. Now, if we conducted 50,000 tests and we got 5,111 positives, then we could determine our proportion of positive data here. Now, we said the other day we want proportions to be percentiles. We want percentages of what we're looking for. And in this case, that's a positive test. How can we convert 5,111 positive tests into a percentage? Well, we can divide that number by how many we have actually administered. So 5,111 divided by 50,432 gets us about, sorry, I thought that was on the screen, but it wasn't, about 0.10, or about 10%. So our p-value, our proportion, is 0.10. That tells us approximately 10% of all people that have been tested have tested positive. So now what we could do at this point is determine how accurate that actually is to the real number of positives. Because what we're saying is we've only tested these 50,000 people, and we're finding 10% of them have the virus. But there can be some sort of error, or margin of error is how I should be saying it, to this number, because of course we haven't tested everyone. So we can determine this margin of error through the standard deviation equation we've been talking about. The square root of PQ divided by N. The proportion of what we're looking for, the proportion of success. Success is a very generous word to be using in this example, but that's we could say. And Q being the 1 minus P, the antithesis of P, if you will, and N being the number of trials. So what we would plug in here is P would be 0.1. That's the percentage of positive tests we've had. Q is the percentage of negative tests, the other side of that coin. That would be 0.9. And then divided by N, the number of tests we've done, 50,432. We can put this into the calculator. So we get the square root of 0.1 times 0.9 divided by 50,432. And we get a margin of error of 0.001. Now, that's a very small number, right? Think about what that is as a percentage. That is 0.1%. So what we could do is we would say that 10% of people have this virus in the state of Missouri, give or take 0.1%. So that means it could be, in all reality, as low as 9.9 or as high as 10.1. A pretty small margin of error, right? That's really, really small. But then you got to think about how small really is it if we're talking about every citizen in Missouri. If we're talking about 6 million citizens, how small is 0.01%? Well, let's find out. 0.01% times 6 million people in the state of Missouri. Let's see. Yep, 6 zeros. That's about 8,000 people, give or take. Quite a few, right? Now, I want you to think for a minute, how accurate of our data set is it for me to make this claim? Because I've made this claim here with this data that based on our number of cases and the number of tests, that 10% of people, give or take 0.1%, so between 9.9 and 10.1% of Missourians are infected with coronavirus. Is this data that I'm using to make that claim accurate for the claim I'm trying to make? Or are there some factors that are confounding it? Well, take a minute to think about that. Pause the video if you want. Is that an accurate claim for me to make based on the data that 9.9 to 10.1% of all Missourians are infected? Well, here's the thing. Why would you be taking one of these tests? We've administered 50,000 tests, right? But under what circumstances are we administering these tests? Did we randomly choose 50,000 people in Missouri to take the test? No, we didn't. These tests are either voluntary in some cases or required based on the advice of a doctor, right? So these tests we're giving out are to people that either already think they have the virus or our doctors believe have the virus, right? You're probably not getting the test, or we're not giving the test to people just for the sake of, yeah, try it out, let's see if you're positive, right? So the information that we're looking at here is not representative of all Missouri citizens, because we are not including all Missouri citizens in the population of who has been tested. We're including all people who are effectively sick, all people who are showing at least one symptom of the virus are being tested, right? So now we could say that there are 10% of people who are sick in Missouri have this virus. Maybe that's a claim we could make. Maybe that's more accurate to the data set we're actually using. But it would be incorrect of me to state that 10% of us have the virus because 10% of our tests have came back positive. Again, because those tests weren't randomly assigned to all possible Missourians. I wanted to mention this, and I wanted to bring this up because this is an important thing we have to think about whenever we're trying to take data and make a generalization about it. For us to make a generalization, we have to make sure that the tests or the trials or whatever it is that we're doing are randomly assigned to everyone in the population. We need to make sure that there are a significant number of tests assigned. And specifically speaking to that, the bare minimum we can do, number of tests we can do to make any sort of generalizations about the population, is enough for there to be 10 positive and 10 negative. And I'm saying positive and negative in terms of something we're looking for and something that is the opposite of that, right? P and Q each have to have at least 10 cases on each front. So bare minimum, we need 20 cases, 20 trials. Now we have way more than that here. But we need bare minimum 20 trials, 10 of each. And we need to have all of those trials to be randomly allocated throughout the entire population. That is the stipulation that this example doesn't meet. But I wanted to talk about some of this data today just with margins of error and calculating it based on information that we don't have 100% accurate true proportions to, but us believing that we are close enough to have that margin of error for. If you have any questions about this, let me know. Otherwise, I'll see you guys in tomorrow's video.